Number 26 is about anols, enolates, the Aldol reaction, and the Robinson annulation from exam 3 material. So let's start by, we are given this structure right here, and we are told to draw the structures of A and B with no further guidance, aside from the reaction arrows. Let's start by trying to figure out what A is. So I see LDA. LDA is a base, so it deprotonates something. And remember the rule about LDA, it is a bulky base, which means it likes to deprotonate from the side or from a carbon that has the most hydrogens or the lowest substitution. It makes the less stable enolate. So for example, if I had a carbonyl like this, it would prefer to deprotonate here. Pull off one of those hydrogens and make that the carbon with the enolate on it. The next step is formaldehyde, so a carbonyl. So let's just draw that out for now, because we'll be using that somehow. And then H3O positive, an acid source, a proton source. Okay, so now I'm looking at this structure here, and I'm saying, okay, so somehow I went from A to this. And now I had to have used formaldehyde, a single carbon. So in this structure, I have to say, well, I have 1, 2, 3, 4, 5 carbons. Which one of those 5 carbons is this carbon right here? Well, since I'm only adding one carbon, it can't be the carbonyl in the middle, because then how did I get these 2 carbons and these 2 carbons attached to it? That wouldn't make sense. There's nothing else over the arrow to allow that to happen. The only place that makes sense for where this could have been added is carbon 1, right here on the end. And why am I saying that? Because this right here, carbons 1, 2, and 3 are trademark, or are a trend that you should always be aware of. There's a very simple way of making something like this. And that is through the Aldol condensation. Very often, if you have 1 and then between 2 and 3 is a double bond, you can make that through an Aldol condensation, which is what we're doing here. Namely, the way the Aldol condensation works is we can try and do this backwards. We say that carbon 1 must have been the carbon that was added. The first step, or the last step of the Aldol condensation is, well, the condensation, where you form a carbon-carbon double bond. And now what was there before, if I continue to number this 1, 2, and 3, before that double bond formed, you had an OH on carbon 3. That OH being the carbon that was attacked by an enolate. And now, if this carbon was attacked by an enolate, well, the only carbon that could have been part of that enolate that did the attack on carbon 3 was carbon 2. So whenever you're going backwards and you have the product of an aldol condensation, what you can do is number the 1, 2, 3 setup, carbonyl on 1, alpha carbon on 2, and carbon with an OH on 3. All you have to do is erase that bond between 3 and 2. And then turn that carbon 3 into a carbon with a double bond O. And would you look at that, carbon 3 right there is my formaldehyde that we're working with over the arrow. Also, look at this carbonyl for a second. How would this react with LDA? We said before LDA is a bulky base, so if I have 2 sets of alpha protons, I'm going to pull off from the set that has the most alpha protons. This carbon over here is primary, which means it has 3, and therefore it is the winner. You'd end up forming an enolate where this hydrogen gets pulled off, the electrons swing up like that, and you'd end up getting a carbon-carbon double bond like that, O-. And then when this swings back down, this will attack the carbonyl, and that will swing up, giving you the O-, which then gets protonated by H3O positive. And while they left out heat, they don't always have to specify heat. They showed you what we're expecting here, and this is the product of an aldol condensation, where the OH ends up leaving so that you can form a double bond, a carbon-carbon double bond between 2 and 3. So the structure of A, based on this reasoning, must be this structure right here. Again, because if this is the carbon that attached to the formaldehyde and then you underwent a condensation, well, that carbon's right here, and here's the formaldehyde's carbon that you added. So here's structure A. Now, what about structure B? Well, structure B looks to me to be something called a Robinson annulation reaction. Why do I say that? Because one, I have this structure right here. There are 2 ways to think about this structure. One is the product of an aldol condensation. And the second is the reactant of a Michael addition. Namely, you have a carbonyl and then 1, 2, you have a alpha beta double bond. It's again, the product of an aldol condensation, but it's also something that does the Michael addition, where rather than a carbonyl being attacked, you end up attacking the carbon, and through resonance, you get an O-. And then whenever you see the Michael reactant reacting with another ketone, and then KOH, or a base really, OH minus or any other base, this is probably going to be the Robinson annulation. So the first step is to say, okay, KOH is a base and it's going to deprotonate something. Now generally it's not your Michael reactant, it's the ketone that you're working with. So I'm going to deprotonate that ketone, and I'm going to look at this and I'm going to say, well, where are my most acidic alpha protons? I have two places to choose, this spot on the right or this spot on the left. Well, OH minus is not like LDA, it's not a bulky base, so it prefers to pull off from the site where the fewest hydrogens are. So that OH minus is going to come in and pull off this hydrogen over here, forming your enolate. And so now I will have O minus, a double bond there, a methyl, and that's it. Now, this enolate that you form will react with your Michael reactant. And so this O minus will swing down, and this double bond is going to go out and attack the carbon at the end of the double bond. So if I were to label this 1, 2, 3, it's attacking carbon 3. Now the double bond between 2 and 3 is going to resonate over to the bond between 2 and 1, and the carbonyl will swing up. So now what is that going to look like? Let's number some more carbons. So we have 3, 2, 1, and let's say this is carbon 4 and 5. So carbon 4 and 5, well, the whole ring that carbon 4 and 5 were part of should stay the same. And the carbonyl that was on carbon 5 should stay this, should be reformed based on this arrow here. So 4 and 5 are there. Now 4 had a methyl on it, and now it's connecting to carbon 3. So 3 was connected to 2, 2 was connected to 1, and we said that the double bond between 3 and 2 is moving to the bond between 2 and 1. For that double bond to move there, that O minus, or that double bond O has to swing up to the oxygen, so now I have an O minus there, and then I have the other two carbons on the other side, so 1, 2. So this would be the intermediate you form from these two, from this set of arrows. Quite a number of arrows, but we're about halfway there now, because the Robinson annulation doesn't finish like that. The next thing that happens is whenever you do a Michael addition, you always end up forming either an enol or an enolate, an oxygen on a single bond connected to a carbon-carbon double bond. And you have to remember that enols and enolates will always tautomerize back to their carbonyl form. So this O minus swings down, and it's going to grab some hydrogen. Where that hydrogen comes from, it doesn't really matter. There's probably water floating around. We had KOH, so there should be some H2O. So I'll actually write just H2O here. And so now I have that carbonyl reformed. So I have a methyl here, carbonyl, and then 2 carbons more. So now we're not done, because 1, I said this was the Robinson annulation and we identified it as such, but 2, if you ever have a good base floating around and you still have a structure with at least 2 carbonyls left over, this is generally going to happen. You're going to keep doing it until you only have 1 carbonyl left, or no way of having those carbonyls react with each other. So in this case, we still have base floating around. We still have OH minus, and he's going to look to continue to pull off protons. So I'm going to look, where do I have alpha protons? I have alpha protons here. I don't have any over here because there are 4 carbons. I have alpha protons here, and I have alpha protons there. And now I'm going to pull off one of those protons, and the carbon that has that proton pulled off will attack the other carbonyl. So if I pull off this proton over here, this would attack 1, 2, 3, 4, 5, 6. So if I pull off this, that makes a 6-member ring. That might be nice. Can't pull off any there. If I pull off this, this would attack 1, 2, 3, 4. I'd make a 4-member ring, so this hydrogen's out. I can erase that. And then this hydrogen would make a 1, 2, 3, 4, 5, 6-member ring as well. So which of these 2 hydrogens is better if they both make 6-member rings? Generally, your rule will be such that you want to use the hydrogen from the carbon chain you added through the Michael addition. The reason being, if I were to pull off this hydrogen, I'd be forming a ring that kind of looks like this. Something along the lines of that. It's not the right size, but you get the gist. And that carbonyl will be sticking out in the middle of that ring, which isn't great. Also, the bridgeheads are 1, 2, 3 apart. We like having our bridgeheads right next to each other. So that hydrogen on the original ketone, probably not the best bet. which means this is the hydrogen you want to use. That OH minus will pull off that proton, you'll form your enolate, and now let's see what we get after that. So carbonyl, methyl, 1, 2, 3, 4, O minus, and then a double bond here to methyl. Okay? And now this O minus will swing down, and this double bond will come in and attack the carbonyl, and this will swing up. Now, based on my numbering before, I said this is going to be a 1, 2, 3, 4, 5, and 6 membered ring. 5 and 6 are part of the 5-member ring over here that isn't being made, so I can just keep those two the same. So I'm going to draw that 5-member ring first. I'll say this is 5 and this is 6. Now, the 6-member ring I'm forming will be between 5 and 6. So I'm just going to draw a 6-member ring coming off of that. And now 5 was connected to 4, which was connected to 3, 2, and then 1 made its bond to 6. Now I'm just filling in the other blanks. 5 has a methyl, 6 has a carbonyl that got attacked, so it's an O minus. Carbon 2 has the carbonyl that reformed. And carbon 1 has a methyl coming off of it. It's a really long methyl. Okay, so this would be the next intermediate I have. And again, well, we're left with O minus, so we're going to protonate that. So we have H plus, well, H2O rather. So that O minus will grab that hydrogen, and the electrons go to the OH. And so now you have the 5-member ring, which you started with, the 6-member ring that you formed, the OH that you protonated, the methyl that was on 1, the carbonyl that was on 2, and the methyl that was on 5. And so now you have that as your intermediate, but is that the final product? It depends on the context of the question. Now, this question didn't really specify too well. It didn't say anything about heat. And generally, heat is what tells you if you're going to do the condensation or not. But that's more particular to the Aldol condensation. In the case of the Robinson annulation, unless we tell you through a molecular formula unless we tell you through the molecular formula or we actually give you the structure, you should assume that whenever you do a Robinson annulation, you will do the condensation. And so what is the condensation reaction part of this? That's the reaction that I was talking about before when we were figuring out A, where you form the double bond between 2 and 3. So start by doing that numbering trick. Carbonyl on 1, alpha carbon on 2, OH on carbon 3. Now what's going to happen is, one more time your base is going to come in and pull off your alpha proton. And that alpha proton will always be the alpha proton on carbon 2, the carbon between the carbonyl carbon and the OH carbon. And that'll grab that. But now, rather than having the hydrogen's electrons resonate towards the carbonyl like we've been doing, it's going to resonate down to the bond between 2 and 3 and kick that OH out. And so this is what the condensation reaction looks like. So this is the one situation where you have OH minus as a leaving group, but the net result is the final product. The 5-member ring that we started with, the 6-member ring that we formed, the methyl on 5, the methyl on 1, the carbonyl on 2, but now a carbon-carbon double bond between 2 and 3. And this is the final product of your Robinson annulation. So again, in the Robinson annulation, if they don't tell you heat, and they don't show you the final structure, or they don't tell you a molecular formula that has more than one oxygen in it, you should assume that you are doing the condensation, where you form that double bond between 2 and 3.